What do we do with these views?
What do you think?
Are we supposed to attach these to lab 1 as well?
Yeah.
So lab 3?
Lab 2.
Lab 2.
Lab 2 is due Wednesday, yeah.
Oh, okay.
Yeah. There you go. All right. So we went over 25, 26, and 27, right? And we kind of just reviewed those. So basically the ones where you're going to need to know how this ties in is that add I is an I type when you do this for lab 3. And you're going to need to know that the opcode is 001000. What's that? I've started the meeting. The meeting has started. I've stopped for some reason, but okay. All right, so it should be up now. Yeah, it's up. So that add I is an I type instruction. And so you're going to have an opcode, and you're going to add a number that's stored in a register plus this number and stored in an RT. So you'll need to know that add I, we're going to be going through Verilog code today, so remember these important details. You need to know that add I has this specific opcode, and you're going to need to know that ALU-op, for those of you who have not had we're going to be going into the Datapath today. ALU-op comes from the controller. It's going to use the same ALU-op as add, and it's going to have this come. So there's going to be no function. It's not going to care, right? We'll see Verilog today after we see the Datapath, and then it's going to send add. So it's just going to add the 2 values that go into the ALU and put it out, and then the control signals do the rest of it. So in your lab, you're going to modify the controller so it can do add I instructions. All right, so how does this multi-cycle data path work? In the general idea, you're actually going to have a combined memory as opposed to what we did in 385 where the instruction memory and data memory are different. We have an instruction memory register and a memory data register. And what's going to happen is, and you'll see this in a second when we have the drawn out data path, is it's actually going to control how it's going to be either reading from the address using an instruction value, or if it's from the memory data register, it'll write data to data memory. So we use these buffers here to prevent the control hazards. So if you remember from 385 when I told you that how they reduce control hazards in pipelining was to separate memory. Well, they ended up not happening because in this case, in multi-cycle, they're combined. So what's going to happen is you have a clock signal, and it's going to go to each of these. Going to go to program counter buffer, IR write, and it's going to combine an AND gate with each control signal. So what's going to happen is in between each stage, so it's going to be in stages, kind of like pipelining, where it's going to put read data out. So it's going to have a buffer A and B. So A and B, they both go to the ALU. And then we're going to see that there's a network of multiplexers here specifically used to do that, to when you have like I-type instruction branches, things like that. So it's going to go to the output. And then all these are controlled, and they're all controlled by the system clock. And the whole goal is that load word is going to be your longest instruction, so it's going to use all 5 clock cycles, and it's going to have 1 instruction in the data path at a given moment. But branches only take 3, as you'll see when we get to the FSM. So the whole goal is to try to reach this compromise between the large amount of area overhead that you get in pipelining and the higher performance the lower performance you get in single cycle. So there are 13 control signals, and I want you all to thoroughly understand these because you'll need to be able to understand these in order to actually do lab 3. Memread indicates where data will be read from memory. Memwrite indicates whether data will be written to memory. Mem to register, that's what happens when you get the value out of the data memory. You're going to send it back to the register, so you have that MDR buffer, and that's typically used in, if it's coming from memory to register, if it's going to be 1, if it's coming from the data memory back to the register, so that's going to be a load word instruction, or in this case, load byte, since it's an 8-bit data path. And if it's 0, that's going to be coming from the ALU, so it's going to be R type or I type. I or D, instruction or data, indicates where the instruction is, where the address is from the instruction. From PC, it's from 0. This comes from the program counter. It's that 32-bit value that indicates it's an actual instruction. Or if it's a destination or data, I should just read data. From ALU out, if it's 1, so that should be data, not destination. IR write indicates where the data will be written to the instruction register. So in this case, what's going to happen, what happens if you have a branch? Are you actually going to change that instruction? Because branching instructions are what happens if you have if statements. So if A equals B, so if you don't meet the condition, you need to branch past the if statement. And so that's how you're going to use IR write. Register destination indicates whether the destination address in the register will be from IR write or the memory data register. So it's going to indicate whether or not you're actually going to write to the register or not. If you recall register destination, we used that in pipelining when we had we're indicating whether or not we were going to write to the registers, specifically which destination we're going to use. You had to select between the R type, which was the second up, and then the R type was the third RT. It was the third 5-bit chunk, and it was the second 5-bit chunk for I-type instructions. ALU source A indicates whether the first ALU source will come from read data 1, that comes from the registers, or from the program counter. So in this case, what it's using is it's deciding whether or not to add the number, the current instruction. So let's say you have to branch past 7 instructions. If it's 1, that means it's going to be branch. If it's 0, it's going to be your typical R type or load or store word, because in load or store word you calculate the address to be able to get that value. ALU source B, this is where it gets more complicated, but you use just a 4-input multiplexer to be able to determine whether or not to use it. So the second value is either going to come from read data 2. So if it's 0, 0, then you're just actually just getting it from the ALU like normal. If it's 0, 1, it's going to be the value 4. Does anybody from 385 remember when we just wanted to add 4? What? Well, you want to add the number 4 is because of byte addressing, but what did we do when we specifically wanted to add 4 to something? If you're adding a byte addressing, that means you're incrementing the address value by what? Well, no. Well, 4 is you're incrementing the number, but if think of it as houses, right? So the analogy I used was houses. So if you're on a street and you have 8100 and the 8110, you're incrementing by 10, but you're only moving one house. So if you're incrementing by 4, you're going to the next address. So you're incrementing the actual address by 1 because of byte addressing, which is what George said. So what ends up happening is you're having 4 bytes and to indicate one instruction. So you have to add 4 to get to the next instruction. So what's actually going to happen here in this ALU source A and ALU source B is you'll get ALU source A is 1 and ALU source B will be 0, 1, and you'll get the current value of the program counter plus 4, and that gives you the next instruction. So that's why you have the value 4 there. So if you have 1, 0 as your input on ALU source B, so it's the sign extended 32-bit immediate, which for lab 3, you're going to want to remember that because you're actually going to be at, in this case, you would get 1, 0 and 1, 0, right? That means you're getting the output from the ALU, from the output from the registers, and the sign extended 32-bit number, and you're adding them together, and that's an I-type instruction. And the last one is 1, 1, or the sign extended 32-bit immediate left shifted by 2. That is, you're actually calculating the branch address. So you're going to left shift by 2 because you're going to multiply by 4 because the number that you're going to add, so if you're branching, you're going to be, let's say I want to branch 7 instructions. So the number is going to be there 7, so you're going to left shift by 2, so you're going to add 28 because each bit, there's 4 bytes require a word for the instruction. So by adding 28, what you're actually doing is moving 7 instructions. So that's why it's left shifted by 2. ALU op, it comes from the controller and goes to the ALU control. So the ALU control, and we'll see this in a second, receives the 5-bit function. And then there's logic in there, which you'll actually be working on in the lab. And then in this case, it's going to send out a 3-bit value to the ALU. I'm sorry, this should go to ALU. Determines the value sent to the arithmetic logic unit. PC source determines whether the value comes from the value sent to the program counter. So there's this multiplexer at the end that comes and goes back to the program counter here. So you're going to want one of the things. You're just going to want the next instruction. If it comes from the ALU, what's actually happening there is you've calculated ALU source A as 1 and ALU source B as 0, 1. You've added the current program counter plus 4, and that's just getting to the next instruction. So that's this case. 1, it's ALU out register. That means you have calculated a branch instruction. So what's ended up happening here is you have 0 as your input, and you have this sign extended 32-bit immediate left shifted by 2. So it's going to be 0 and 1, 1 is going to be combined when you have PC source equal to 0, 1. And then the 32-bit jump address is actually calculated by using 26 bits. You remember in this last instruction here, when we talked about this, right? This 26-bit address. What's going to happen is this is the number of, this is the current instruction you're going to be. So what happens is you're going to left shift by 2 to multiply by 4. And then that's going to give you 28. And then you're just going to concatenate the 4 most significant bits of the program counter onto to get 32. It's typically just going to be 0, 0, 0, 0. You've written quite a program if you're getting up to the 29, 30, 30, and 31st bit of the instruction. That means you've written literally trillions of lines of code. Probably shouldn't do that. You've written more lines of code than it's in an operating system. So, and then okay, so PC write. You're going to OR it with the PC write condition to determine if PC will be written to. So in this case, you need to determine whether or not you're going to overwrite the program counter. And then PC write condition is going to be ANDed with the 0 from the arithmetic logic unit. Now, for those of you who didn't have me for 385, the reason why we do this is because there's a situation where you might actually have, if you're doing a comparison in the ALU, you're going to get a 0 bit that's going to come out, and if that meets that condition, then it's ANDed with the actual branching control signal. So what could happen is, let's say you have some sort of comparison that's not a branch instruction, and you need to tell it whether or not it's a branch instruction and the condition is met. And we'll see that when we go to the data path here in a second. It has to be ANDed, otherwise you may have instances where you have something called a control hazard where you might branch even when you don't want to. and then it's going to go OR with the PC write, and we'll see this in a second, to determine if the program counter will be written to. All right, so I'm going to zoom in on this. Here's my zoom here. So make your own version of this data path on your lab submission. Actually, you know what I'm going to do? Everything that we covered up till last lecture, just put that in lab 2, and starting with the control signals and the data path and everything in section 8, put that in lab 3, because that's more appropriate for lab 3, because everything that we're doing on this point should be helping you get through the Verilog code to complete that portion of the lab. So here's what all that jibber jabber I was just talking about means. So here we have our program counter signal, right? And so this is just the clock signal, so it's a little buffer that's holding it. See, one of the things I got from people who've interviewed at Intel recently is that when they're actually asking you to draw up data paths, that they're actually paying attention to whether or not you draw these little clock signals. So that's a little triangle that's just indicating that, for those you've done flip-flops in the past, right? So that's just the same thing. So especially if you're drawing like a pipeline or data path, you're going to want to be attentive to this. So instruction or data, so let's say it's 0 because that's what the basic is. So if it's 0, then you're going to get the program counter address that goes to memory, right? And then you're going to get that value out. That value is going to go to both of these buffers. And here's a clock signal it's going to hold. So IR write, instruction write. So what this means is that you're either going to want the instruction to go to data memory, or you're going to want to update the register here. So what's going to happen is in the first cycle, so we're going to be drawing this finite state machine. So you're going to have a set of initial stages. You're going to want IRD to be 0. Right? Because you're going to want this to go through. And you pretty much want the rest of these to be 0, because it's not going to go past until we hit this clock stage. So you get to the second stage, instruction fetch, instruction decode. You want to IR write to be 1, because you're going to want all these values to actually be put through, right? And you're going to want mem to reg to be 0 and reg write to be 0, because you're not going to want the registers written to. And then register destination is going to be based on that. Ultimately, it's going to, in the FSM, it's going to be a don't care. Because if you're doing reg write, it doesn't matter where you tell it to go, and it doesn't matter what you tell it to write. If it says don't write, it won't let you. So register write goes to these registers and indicates whether or not it's going to be written to. And then you got a clock signal that holds these values out, right? So what these are going to do is that it's going to hold A and B out from these, and it's going to be sent to the arithmetic logic unit. So that big, those 2 topical guide objectives where I talked about ALU source A and ALU source B, here's what this means. So if it's 0 for ALU source A, we're actually getting the program counter coming along here and going to ALU source A. And when I say it's 4, it's going to take 0, 1, and it's going to add these together. And then it's going to go, I'm sorry, it's not going to go this way. It's going to be held at the clock, and then it's going to go to 0, 1, and it's going to go back around to the program counter, in which case it's going to determine whether or not it wants to write. If we just want to add the 2 values, what's going to happen is you're going to get 1 coming from the ALU, and you're going to get 0 from ALUB. See? If you want to do add I, and this is what's going to be important for your lab, you're going to add the first value. It's going to come from the ALU. So it's important to note that ALU source A is going to be equal to 1. If it's B, what's going to happen is you're going to get the last 16 bits from your instruction are going to come through here. You're going to get sign extended, so it's 32 bits. So if it's a positive number, you can just do, it's going to look at the most significant bit and just add that 16 times, right? So if it's 16 bits and it's the most significant bit is 1, that means it's a negative number. So it's just going to add all ones, otherwise it's going to add all 0. So it's going to take that value. It's not going to shift left 2. It's going to come here. And it's going to be 1, 0. Then it's going to add it. And then that value is going to be written back to your register. So it's going to happen here. It's going to come back through here, right? And the control signals are going to be such that it's actually going to write back to the registers. Oh, I'm sorry. It's going to take this value here. And let's go back to mem to reg, right? Its memory to register is going to be 0 because we're not getting it from memory, we're getting it from the ALU. And then it's going to write data. And then what's going to happen is the second, so this is going to be R, if you look back, this is going to be RS, and this is going to be RT. So what's going to happen is register destination is going to be 0. These 5 bits are going to be sent to write register. If you recall from last class, that goes to a 5 or 32 decoder. And each of that result's going to be used as the word line on your SRAM. And then these are the values that's actually going to be indicating whether or not that's going to be your bit line results, right? So word line, right to the SRAM. Each of these 32 is going to go to each specific SRAM, and it's going to say this is my bit line, so you can actually determine which way it's going to loop around in the SRAM cell. And then last, if you actually want to branch, what's going to happen is you have to branch a certain number of instructions. Shift left 2 is going to be multiplying by 4. And so that's where 1, 1 is going to come in. And so in that case, you're going to have program counter. You're going to get through 0. And it's going to go to the ALU. In which case, we also want that value to get. Now, the reason why we have this here is because instead of waiting for the clock signal, if we realize we have to branch, we don't want to do anything else. If we let it go another clock cycle, what's going to end up happening is that you're going to go to the next instruction, which is going to be the first instruction inside that if statement. We do not want to do that if we want to branch. So if we want to branch, we want to go past all of them. So what we're going to do is we're going past the clock, and it's going to go straight to program counter and saying, hey, wait a minute, I need you to update this immediately. Otherwise, we're going to have a control hazard. And then these are the basic things that are going to go here. 31 to 26 is the 5 most significant bits. For it's 0, 0, 1, 0, 0, 0 for add I. Remember that because when we go to the next section, that's going to be important. And then what's going to happen is you got your PC write. Either the PC write is going to be done, either I want to update this if PC write is true, or if I have a branch condition, I'm going to say it is a branch instruction, and if the 0 bit comes from the ALU, then the condition is met. If that's the case, then I'm also going to want to update the program counter as well. All right, so that's that data path. I've posted all the rest of the notes for the semester on Blackboard as well. So section 8, this is kind of, you're going to see we're going to develop the finite state machine here. And then you're going to modify the finite state machine in your lab report to include an add I instruction. And then when you do that, then we're going to go through and we'll say what should we add here, what should we add here. And you'll eventually see that by modifying the Verilog code, which you all know because you did Verilog, then you'll be able to actually modify your given code to be able to update this. So, instruction fetch. So, like I said before, I want to fetch the code. So, PC write. I want this code. I want this value to go here. So, I or D is going to be 1. going to come through here, and it's going to go to the instruction register where we had that IR write signal. Everything else is 0. I don't want the ALU source A here, 0. I want the previous instruction to come from here, and then 1. So that means we're incrementing the instruction and getting that value. So what's going to happen is the first stage of this finite state machine, like we said, IRD is going to be 0, mem read and mem write. If it's like this, it doesn't say if it equals 0, that means it equals 1 in there. So mem read is going to be 1. That means I want to get the value from the address that's indicated. I'm reading from there and putting it onto the IR write, which is also going to be 1. Does that make sense? That's the most common question I get after the lecture on the FSM is, what does it mean if it doesn't have a thing on? So this means it equals 1. And so ALU source A is 0 because you're getting it from the program counter, and ALU source B is 0, 1 because you are getting the result of the previous. You're incrementing 4 to get the bytes. And so instruction decode, this means I'm actually putting it here. This is not the most well drawn out diagram, but basically you're getting all the values, RS, RT, RD, you're putting all that values and you're getting them out, right? And so it's going to have, the key thing you need to know is ALU source A still needs to get the next instruction, right? So it's still getting it from program counter. And then from here, we're shifting left by 2 in the event that there's a potential branch instruction. Now what's going on is that we want this branch to be able to go back really quickly. So they actually, in this stage, we actually calculate the branch, a potential branch instruction, and then we wait to see if it's actually a branch by using these instruction decode or PC write condition values. So since in every other stage would be using the ALU for everything else, it's designed such that we have that value ready to go in the event that we actually might need to branch. And so our second stage of FSM, we calculate the branch instruction. ALU op is 0, 0 because we need to add. And then PC write condition is 0 because we don't overwrite it yet. And so what's going to happen, you'll see this, is it's going to start splitting up. We have R type, load word, store word, and J type, and all that other stuff. So ALU is going to perform one of the following functions depending on what we actually get out of it. So it's a memory reference. Okay, so like I described before, we're just adding the RS value and the sign extended offset. R type, we're just adding the values. Branch, if A equals B, this is an example, the program counters are going to equal to the output of the ALU. And then jump condition, as I've described before, is just we concatenate the shift left, and then we concatenate the 4 most significant bits. So this is the shift left, and then this is the concatenation of the 4 most significant bits of the program counter. So load word and store word, as I described, we get the first value here, and then we get the value to calculate our output. That's going to eventually come through here and go to the address that we're going to write to. Yeah, I'm sorry, here, right address. I'll get it right eventually. There we go, right address. That's what we're calculating here for load word or store word. And then R type, we're just getting the values here. We're getting ALU is going to be A1. It's going to be 0. The thing that was not going to be drawn out, but it's going to be important for your lab 3. If it's write type, it will come through 1 here, or it will come through sign extended, will not be left shift, so it'll be 1, 0, and I'll go through there. Branch equivalent, we already have the value calculated, so if we decide we are actually going to branch, we put it on the ALU out, and that's going to go to the next stage. So we're going to use 0, 1, here. PC source will be 0, 1. And then PC write condition, we're going to have the branch and the 0 bit. Remember this 0 bit I was just telling you about? So in this case, what's going to happen is if it's actually a branch, we'll get PC write condition, and that 0 bit will be ANDed, which will automatically satisfy the OR condition and then update the program counter. For J-type, you're basically getting the 0 to 26 here. You're shift left by 2, and you're getting this value from, this is the program counter here. You're getting the 4 most significant bits, and you're concatenating. So it's not the most perfect drawing. And you're getting this value 1, 0, and it's going to go here. And that's the address you will jump to. Okay, so this is the new updated FSM to this point. So load word and store word, you're adding the output from the ALU register and the 32-bit. Adding, ALU op is 0, 0. PC write condition is going to be 0. PC write condition is going to be 1 in the case of branch equivalent. For R type, you're not writing to PC, so you're going to get 1, 0, 0. It's coming from the output of the A register. 1, 0 for ALU op. Because if it's an R type, it's going to go there and it's going to use the function, the last 6 bits, to determine otherwise. And then jump PC source is 1, 0 and PC write. So quick question, because this is going to be the next, if I wanted to add one here for add I, what would my values be? But I'll step out for a second. In your groups, I want you, because this is going to be the next problem, figure out that FSM. Actually, you know what? No, I'm going to delay it. And what I'm going to do is I'm going to put the problem up and let you all have like 5 minutes or so to actually add the full stage of all the specific things you'll need to do. Better idea. Okay, so stage 4. This is what's going to happen here is we have now calculated our results. Now we need to start updating values. So what's going to happen is load word and store word are going to split up here, and then R type is going to update the register. Branch equivalent, now you're going to actually have these values actually go back here to the start because it is an FSM, because we've calculated everything we need for these. So for Datapath activity, IRD, instruction or data, it's going to be 1 because it's data. So load word, we actually are we're getting value from the memory and putting it to the register. So we have this value here that we have calculated the address, and it's going to this address. It's getting this value, and then it's going to put them both here. What's going to happen is IR write is going to be 0, to say that is not an instruction. And then MDR is then going to put it, we'll get to the final stage here because we've got the clock here. So it's going to hold that until the final stage. But it's eventually going to go through write data. During store word, what's going to happen here is we have calculated the address. It's going to come out of ALU out, and it's going to go to here. IRD is going to be 1 because it's data. It's going to go to an address. At the same time, for those of you who remember, store word is getting a value from a register. In this case, it's going to come from read data 2. It's going to come through B and go back to write data. And in order for this to work, we need memread to be 1. I'm sorry, memwrite to be 1. Does that make sense? For R type, what's going to happen here is you have the result of from your calculation from ALU out. It's going to come here. this control signal here is mem to reg. So memory to register, if you're writing it from the memory to the register, in this case it's a load word, and we'll cover that in the final stage, it would be a 1. But just it's coming from the arithmetic logic unit in the case of an R-type, or for your next thing, if it's an I-type instruction, it'll be a 0 for add I. And so what's going to happen here is we're actually done with branch equivalent. We've calculated the address. We're also done with jump. So what's going to happen here is it's just going back to the beginning again. So the finite state machine is started. For R-type, we've turned register destination is 1 because we are getting it from we have RS, RT, and RD, right? So we need it to be 1 to differentiate those 5 bits. Register write, we're of course writing to the registers. Memory to register is 0, and PC write condition is 0. For store word, we are writing to memory, so it's is 1. IRD is equal to 1 because it is data. And PC write condition is 0 because we are not updating the program counter. For load word, we are reading from the memory because we're loading it to the register. Instruction or data is equal to 1, and then PC write condition is equal to 0. So last thing we're going to do is going to add one more stage here for load word. So what we need to do is we actually need to load the value from the actual data from the memory into the register. And so what's going to happen is you're going to have reg write is going to be equal to 1. You're going to have the specific value for mem to reg is going to be 1 because it's actually coming from the memory to the register. And then, as you can see, we are indicating our write address, and it's going to be 0 because it's going to come from RT in the I-type instruction. So you have opcode RS and RT, and then the 16-bit, right? So it needs to indicate that it's coming from RT, which is why this one is 0. It's from reg write, so it's 1 there. And then we need to write to the registers. Okay. So what you're going to do is, so this is the full FSM. So what I'm going to ask you guys to include for TGO 8.1 is you're going to produce this FSM and you're going to modify it to include an add I. Now I've also I'm going to step out for a split second and let you guys work on it in your groups. I've also posted the section 8 lecture notes. I know that the answer is on page 8. So, but I want you guys to actually kind of see if you can think through it and think like an engineer. So also the other reason why you can go on there is because on the previous pages, especially on page, you can go to section 7 where I have it drawn out. But you can go through the first 7 pages and take a couple. I'll give you guys. It's 9. I'll give you till 9:45 to modify this FSM. So all I want you to do, obviously, I'll give you a big hint. Up to this point, they're all the same. So what's going to branch off is going to be here, here, and there. So there's values that are going to be in those two. So see if you can figure out those are. So all that's available on Blackboard as well. So I'll step out, and so you also don't feel pressure.
That I was resting on my business next. I send it to you. When yours is off too. Where's your video? Which part? All video and all.
Like, you know, my Wi-Fi.
Yeah, but you look at them, it doesn't have. Let me go to charger. Charger with me. I mean, is it like they are on group or like
Yeah.
That's why I was like, oh, I guess you don't want to work with her.
Good work, Mike Boy, helping out George a lot.
Is it kind of like the
Yeah, it's just kind of,
I'm not sure about the source, but I know it's got to be something.
where does 0, 1 come from? You know, 0, 1 just added 4, right?
The AI.
Very good. Good catch on the ALU walk, by the way. That's who when I did this last switch that everybody missed. You have to add. You have to add. For the ALU walk, no, the ALU walk is just the value that's being sent to the function.
That's actually after.
Yeah. So.
All right, well, it's 9:50, so Bo and Meisha, since you got this, you guys got this port right here, this particular node. Tell everybody what the values that you got.
First, the ALU source A would be 1.
Correct.
And then source B would be 1, 0. It's going to add immediate.
Right. So what they correctly noted is that here the value is actually going to, instead of coming from this source, it's actually going to come from the 16.0. It's going to be sign extended. It's not going to be shift lefted by 2 because you don't have to multiply it by 4 because there's no byte addressing. You want the actual value. So it's going to be 1, 0. And that's going to be sent to the arithmetic logic unit. So it's going to be ALU source A is 1 here. Right? So that's that particular stage. So let's see if anybody came up with the clever solution to this. So once you've calculated the value of the arithmetic of the add I, do you need it anymore? So what? No, you've calculated you've made the calculation with the ALU. You've got the immediate value. So is there anything else different between the add I and an add instruction after that? So typically, clever solution was I'll just put this node here. So go here. What I would like you guys to do for 8.1, when you include this in lab 3, is, and you'll see why when we go through the Verilog code here in a second. You're just gonna do this, but you're gonna add it. I call it state 13 because there's already 12 states, right? So you're gonna add that node here. We have ALU source A is 1, ALU source is 1, 0, and ALU op is 0, 0. So you guys got it right, Bo and Meisha. Good job. Did anybody else put that down or come close?
Okay. So I will give on exam 3 points to Bo and Meisha for getting their answer, and then 1.5 to Josh. And Josh, you have a partner? No. Okay. Well, 1.5 to Matt and Josh.
That's where you go, shh. That's where you realize that that's another better is the enemy of good enough. Don't go there. I don't deserve credit for that. Don't say that voice issue with the professor, otherwise he might take my points away. So he might never let me see the dog again either. So, okay, so, and then here is the actual, I don't include this, but I want you, I made them do that in 385. This is a little too much. But basically these are, when you put these all together, that translates into these in the binary code. Sometimes I've noticed some people will struggle a little bit with FSM interpretation. I do want you to include the FSM in 8.1, but for those of you who seem to do better with binary, I don't know if anybody's like that. Here it is for you, so that way you can actually go through. So 1101 is actually state 13, so you can actually use AO source B or source A. So you can actually add a 13th state here, and you're going to be coding this into the Verilog, so you can use that as a reference. And so basically how this ends up working is you have these state registers which contain the 4 bits which correlated in this to these right here. And so the FSM tells you which the state to go to, and you start out initially with this opcode. And so based on the specific states, it'll go through, it'll traverse the FSM, and then based on that, it will output the appropriate control signals. So here's the actual, in your lab, you're going to modify the controller.v. So we're going to go through each part, and then you're going to tell me what you think you should modify it as. So here's all his commenting, because he's a good coder, because he has commented properly. And so he has all of his inputs defined. So he's got his opcodes, his 0 bit, a reset bit in case you want to start everything again. So then his outputs, he's got memread, memwrite, so he's got all of these control signals. PC enable, which is the output. Let me scroll down here. ALU op 0, ALU op 1. So the whole point is you want to be able to have the controller feed in with the rest of the data path, right? So the control and the data path are going to be 2 Verilog modules, and they're going to communicate with each other. And that's typically how it's done. For those of you who had 3, which most of you have had 386 at this point, you're familiar with that. You split it up into controller and data path. So this is going to be the controller. So the multi-cycle, so each one here, so you have those 4 different fetch stages, right? Those are all combined into one. So decode, memory address, load, write, R-type, execute, R-type, write, branch execute, jump execute. So what would you need to do here in lab 3 to modify this for add-I? Since you guys just came up with the state, you have to add one more state. Yeah, parameter. And you specifically want, well, we're going to be coding up the instruction value here. So you can call it add-I to maintain everything, add-I execute. The reason why is this parameter here, this R-type execute, is when it takes the value from ALU A is 1 and ALU B is 0, 0. You're modifying that. So I would say parameter add-I x equals 4, 1, and we call it 13, right? So 1, 1, 0, 1, colon. So that's how you modify it there. So instruction opcodes, how would you modify this to include add-I? Think back to your TGO table, specifically opcodes.
0, 0, 1, 0.
So this is where you could just call it parameter add-I equals 6. So binary becomes 0, 0, 1, 0, 0, 0. If I'm correct, which I'm pretty sure that is the right. Yeah. So your internal signals, you need to add one more here, right? Well, okay, so you got this one. These are the control signals. You don't have to add any control signals to modify the data path. So you don't have to do anything here. So they have this master and slave register. That just indicates the next state. Next state logic. So this is where you need to add one thing. You need to add 2 lines here, right? So here you have fetch 1. This is going to have next state fetch 2, next state fetch 3, and that correlates here to this one here, right? Fetch 1, fetch 2, next state's fetch 3, fetch 4. And so what you're going to do is you're going to modify this state here, fetch 4, to have this, and then you're going to want to do those two, right? So you want to modify that so that way add I, the next state is going to be, you're going to eventually want add I, next state S2 is going to be R type right, because they're the same. But you need one here like mematter where it splits up. You're going to want case op3 is equal to 0. I mean, op3 is going to be equal to 1. The rest equal to 0. And then have it go to add IX. Does that make sense? So you want to have a case there. So decode case op5, op4, op3, op2, op0, right? So this goes if it's R type X. So what you're going to do is you're going to add I here. Next state S2 is equal to add IX, right? And so normally for decode this R type X here, what you're going to want is to modify that to include a case where it just, oh no, I'm sorry, if it's add IX, right? Is just going to be equal to next state R type right. So you're actually going to just add a line here, add IX, and then copy this because it's going to the exact same state. So does that make sense?
So do we still need the case?
Yes. Oh, you mean like, oh, case? No. I see what you're saying. No, you don't need a case. You just add that line. Add IX, colon, next state, because it's actually just going to the next one there. But you need to add this portion to this case here. Does that make sense? So this is where understanding the FSM and understanding the data path makes the very simple. So this is where the default signals come in, just at like the initial case. So fetch 2, fetch 3, see how they're adding everything here. So here you're going to add an add IX. Make sense? So here you add ALU source A is 1, ALU source B is 0. So here it would be 1, 0, right? So you're just kind of getting it from a different case. ALU op is going to be 0, 0. Why is it 0 and not 1 like they have it there? The short version is because when you use a 1 in R-type instructions here, because it makes the decision for all R-type instructions, you can see that in the 6-bit function at the end of the instruction. Since it's an I-type instruction, we just want it to add. If you want to force it to add, you change this ALU op to 0 here. So your add IX is going to begin. So ALU source A, just like that before. ALU source B is going to be 1, 0. ALU source B is going to be 1, and ALU source B bit 0 is going to stay 0 like that, right? And then ALU op here, this one's going to change to 0, and that one's going to stay 0. So then you just add that here in that particular place. And then from there, okay, so I'm debating what to do here. So this is the end of what you'll need for that part of lab 3. Everything else in this section is about physical design flow. There's no real problems. It's kind of more how do you actually take everything out from the pad frame up through, it's basically the rest of it. So what I would like you to do is when you do lab 3, include all the TGOs from section 8. So the short version, I'll skim through it, and then y'all can go into more detail. Anything that would be on an exam would be just like a definition. There's no actual like combining concepts problem. Because I do want to spend next week on what I have as section 9. It's testing and robustness. And we're going to be covering something in detail next week called the D algorithm, which will be on your take-home exam, which I consider that specifically to be really important. So the general idea is where you kind of, up to this point, you got your Verilog net list, and then there's been a bunch of stuff from this design automation process. So we've learned a lot about dealing with interconnects and timing and design. And so what's going to happen is we're going to discuss a concept called floor plan. So you actually figure out how to lay it out on the chip, and then you figure out how the timing works based on that flow to ensure all your wires are set up properly. And then you're going to optimize synthesis, and then you're actually going to come up with a circuit. And so there's 7 steps. Design entry, you enter the design. Synthesis, you're using a little more than interconnect loading, kind of what you all did with WinSpice. Actually, precisely what you did with WinSpice. So you're developing a net list based on, so you remember you came up with you put in a bunch of nodes for NAND gates, and it actually did a SPICE net list. So that's the synthesis part right there. It's actually laying it out for you. Initial floor plan, then you're actually kind of laying it out. Synthesis with load constraints, so you want to make sure you're meeting all the capacitances and wire constraints based on the actual underlying technology. Timing and timing-driven placement. Remember, we designed you have to make all of the you have to make your noise margins. In order to do that, you had to deal with all these different timing constraints, and we did a lot of these problems about how do you calculate timing and when you need to add buffers. So that's often done here. Synthesis with in-place optimization. So you actually laid it out there. You actually lay out all the pins. So if you did something like this, it would actually lay out that. Remember in lab 2, you did the arithmetic logic unit, and you put all the nodes together, and you laid it out with different. You had the 80 lambda from the VDD to ground constraint. So you put in those constraints, and it lays those out for you. And then it goes into details and actually uses like that raster-based node extraction to be able to make sure that you've laid it out properly and meets all the constraints. And this is actually kind of just the flow chart of what I just described here, where you go back if it doesn't meet your timing constraints, or you also make sure that your net list meets your noise and reliability. So you have to make sure you meet your noise margins based on your supply voltage and capacitance. Floor planning, and so this is the actual floor plan. When you actually, in lab 3, you actually are going to synthesize the full data path. You're going to take that modifying and putting it in there. This is what the floor plan is going to look like, where it's right here in the middle. That's optimum, and these are the actual lambda sizes of the data path and control. And then you actually have these 8-bit slices. And so it's actually go through here, and it actually has a wiring lambda constraint, right? So remember, in your lab 2 is 80. So for the controller, it's 380, and for the data path, it's 320 lambda. And so it does these bit slices to optimize the logic flow. And so now that you've actually gone through this, you all understand your IR write bits, your ALU, MDR, so where it actually intersects here. That's where the control signals are going. Register names, and you've got all these different pieces in there. All the different AND gates, the adders, everything you need to build up the circuit. So floor planning is a mapping of the hierarchical net list describing the circuit in its physical description. So if you think about the analogy for those of you who had 3D5, the difference between architecture and organization, the architecture with the basically you have the code and you have your underlying hardware. And a lot of times computer scientists will deal solely with code and never realize about the hardware. And the hardware people will try to optimize it without worrying about how to compile down. And the computer architects take those system attributes that and combine them together. So floor planning is where you have the same location between the net list and the actual physical description. And then floor planning algorithms arrange the blocks on the chip, decide the location and specifically what input-output pads you'll be using, decide the location and the number of power pads that you need. So the power pads actually bring in your supply voltages that you need, especially if, remember, we use voltage at different voltage stages in order to try to reduce power consumption. So if you need more than one of those, if reduction of power is really important, that's when you're going to be using a number of different power pads. You want to distribute the power. Remember, you don't want to use up too much of one specific area of the silicon and not use others. So you have to worry a lot about power distribution, and then decide the location and type of the clock distribution. So especially when you get below 0.13 micron, this should seem more intuitive, especially as you're doing pipelining or multi-cycle, where you have to have a lot of different clock signals going to your registers, going to your buffers, and each one has to be ANDed. Now in modern CMOS, and I think one group even kind of, if I recall correctly, wrote one of your semi-wiki articles about this, about how the clock signal is now the main power consumption within the circuit. So typical layout densities, these are important so you just understand, like SRAM and DRAM, 1000 lambda squared per bit, because you have to deal with 32. DRAMs are smaller, read-only memory is about the same size. Data paths, this is for the MIPS that you're going to be working on in your lab. Types of floor planning tools. It's 1010. I'll skim over this in more detail next Monday. Does that sound good? So it's available. You guys can, when you do it I'll skim over it again, section 8, and then we'll hit section 9, and then you all can put that into your lab 3, and if you have any questions about section 8. But this is really straightforward. I mean, the example question is just basically when we get into this, how do you split it up? It's going to actually use a tree, and I'll go over this next lecture. It's going to have a little tree here to determine how to actually slice these up, how to actually cut through to ensure, because this is where you're going to want to route the wires, right? So it starts here. So, okay, I got a full way through, and then I got to build the tree, and based on that, it's actually going to develop this. You're going to route the channels in the order here in section C. Does that make sense? I'll go over that in more detail next class.